Hello. Today we're going to look at Taylor polynomials. So this will be a way we can express a function, at least approximately, as a polynomial. Okay, so we'll leap straight into our definition. So these are actually two definitions, definition of a Taylor and a Maclaurin polynomial. As we'll see in a second, the Maclaurin polynomial is actually just a special case of the Taylor polynomial. Okay, so our Taylor polynomial of degree n of a function f, and we say it's centered at x equals c, is given by this formula. Okay, so our polynomial, the first term, the constant term here, is just the function evaluated at c. And then we have the first derivative of the function evaluated at c multiplied by x minus c. And here now we start seeing the pattern. It's a second derivative evaluated at c divided by 2 factorial, then x minus c squared, and so on. And so you can see then it's a third derivative divided by 3 factorial, x minus c to the power 3, and so on until we get to the nth term, which is the nth derivative evaluated at c. We divide that by n factorial, then it's x minus c to the n. Okay, and I say now the Maclaurin polynomial, imagine everywhere we have a c here, we essentially just replace that with a 0. So obviously each of the x minus c's just becomes an x, and instead of f of c and f prime of c here, we just get f of 0, f prime of 0. And so as a result, the Maclaurin polynomial is centered at c equals 0, and that is given here. And again, it has degree n. Okay, so there's the definition, and we'll leap straight into an example to see how we can do this. Okay, so let's take the Maclaurin polynomial. Obviously, because it's centered at c equals 0, the Maclaurin polynomial is a little easier, so we'll start there. We'll take the function f of x equals e to the x. Maybe we'll just pop the formula at the top here. There we go. And we'll find the Maclaurin polynomial for that. I think we'll just go to degree 4. And so as I say, we need the derivative. We need the first, second, third, and fourth derivatives here. And e to the x is about the easiest one we could do because, of course, each of the derivatives of e to the x is simply just e to the x. And if we evaluate those at 0, f of 0 is 1, but of course f prime of 0 is also 1, and so on and so on. The fourth derivative of 0 is even 1. Okay, so that gives us that each of these coefficients should be 1, and then divided by the appropriate factorial. So the first one is f of 0, f prime of 0, f double prime of 0, 2 factorial, and so on, each of the coefficients. And so we just plug in, we're going to get 1 plus x plus 1 half x squared, 1/6 x cubed, and then 1 over 24x to the 4. And I say this is the Maclaurin polynomial of degree 4. Obviously, we could take more and more powers, and the higher the power we take, the more accurate an estimate for the function it is. Okay, and let's think about what they look like. Okay, we're saying that this is an approximation for the function. Well, how good an approximation is it? Okay, so we have two lines here, the red one and the pink one here. The red one is the e to the x, and this one here is the polynomial. It's the degree 4 Maclaurin polynomial centered at 0. And what you'll notice is, as we're very close to the value we're centered at, in this case 0, the estimate, the function is pretty much exact. In fact, at 0 it is exact. So imagine if you plugged in 0 here, of course this would be 1, and this is obviously also 1. But as we get further away from 0, the estimate becomes worse. Now obviously on the left hand side it becomes bad pretty quickly. On the right hand side here it's not so bad, but obviously as we get further away from 0 it gets worse. And if we see the same thing but further away, the gap gets larger as the x's get further away from 0. Notice here the scale on both axes is a little smaller. Here it's larger values of x, so it's a little bit further away. Okay, but still this is a reasonable approximation for the function e to the x as long as we're close to 0. Okay, let's take another example. Let's take a Taylor polynomial of degree 5. So we're going to get an x to the 5 term. Our function is x to the negative 1, or 1 over x if you prefer, and it's going to be centered at c equals 2. So this time we're going to plug in 2 to all our derivatives, and again we're going to take all these derivatives. Okay, we'll take the function itself, first, second, third, fourth, and fifth derivatives. I've also, just to sort of show how it works, we have the nth derivative here, As you start seeing there's kind of a pattern, they alternate. The first one is plus, then minus, plus, minus, plus, minus. Also what we're doing, we're bringing this power down each time, so that 2 comes down, the 3 comes down, the 4 comes down. And what that's actually creating is a kind of a factorial term here. You'll notice the factorials 1, 2, 6, 24, 120 are actually the factorials. So we will take the n derivative, we get the n factorial in there. But we also need to plug in the 2's. So we plug in f of 2 is a half, f prime of 2 is 1 over 2 squared, f double prime 2 over 2 to the 3, and so on and so on. And again, you'll notice, as we've done previously, I'm not simplifying here. You clearly could simplify, some of the terms cancel, but I think it's easier to see what's going on if we don't simplify. It's pretty clear that the numerator is that factorial term again, and the denominator is 2 to the power n plus 1. Whereas simplifying it might be not clear to see what that is. Okay, so those are our terms. Remember, we also need the factorial term, so we plug everything in. We're going to get this. So x to the power negative 1 can be approximated by, well, our first term is just a half, then we get each of these factorial terms, a 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and we get each of the terms we just found previously, which is the 1 factorial over 2 squared, 2 factorial over 2 to the 3, and so on and so on. And this time, instead of just an x here, we have an x minus 2 squared, x minus 2 cubed, and so on. But now clearly we can cancel. We have the factorial terms in the numerator and the denominator here, so they can just kind of disappear. And we're left with this. We get 1/2, we get 1/2 over 2 squared, 1 over 2 squared, x minus 2, 1 over 2 cubed, x minus 2 squared, and so on and so on. We also alternate, we get the plus minus terms here. So this is the Taylor polynomial of degree 5 for the function f of x equals x to the negative 1 centered at 2. Again, if we turn a look what this looks like graphically, and actually we'll take just the first term. So instead of the whole polynomial of degree 5 that we had, which maybe we'll just pop down here, this is just the Taylor polynomial of degree 0. So it's just the first term, which obviously isn't very accurate, but gives us a half. And if we plot those two, well, we have the line isn't great. Of course, it's just a horizontal straight line. But we do notice it is exact at 2. Okay, that does give us the exact value, but then it's sort of off. But if we keep going, let's take the next term. Okay, it's still exact at 2, but it's now starting to pick up the slope of the curve just a little bit around here. So it's a little bit closer as we get closer to 2, and then as we keep adding terms, so that's the polynomial of degree 1. This is now the polynomial of degree 2, and you can see it's a little bit better. And as we keep adding terms, it's a little bit better. Still not perfect, but a little bit better, and still very good as we're close to 2. Of course, still perfect if we're at 2. There it is of degree 4, and finally that's our last one of degree 5. And again, if we're around the value of 2 here, this is a very good approximation for 1 over x. Now if we're far away, not so much, but close to 2, it's very good. Okay, and then our final example, we'll take one more example. We'll take a Taylor polynomial, this time of degree 4. Our function is going to be root x, and we're going to center this at x equals 4. Okay, and we're going to use this to approximate root 3. Okay, the point of these things is, finding a square root might not be trivial, but plugging a value into a polynomial is pretty trivial. And because 3 is pretty close to 4, we might be able to get a reasonable approximation for root 3 using this Taylor polynomial. Okay, so once again we have to take all these derivatives, so we just take f of x. Because we're looking at degree 4 now, we just take the first 4 derivatives, so we take root x, and we differentiate each time. Obviously it's a little more complicated. And then here on the right hand side we just plug in 4 to get the value in each case. Okay, so now there we go. So we've got each of these coefficients, the 2, the 1/4, the minus 1 over 32, 3 over 256, and so on. Always remember we have to divide by the factorial term. This is often the most common mistake. People just forget the little factorial term there. And again, because it's centered at 4, this time we get x minus 4 squared, x minus 4 cubed, and so on. And now we will simplify that. Okay, give it its own line. And there we go. there is our Taylor polynomial of degree 4 for the square root of x. Okay, and we did say, well, can we use that to approximate root 3? So let's plug in 3. Let's just basically plug 3 into this equation. Okay, and actually that's pretty simple to evaluate, and we get that if we plug 3 into here, we get 1.73212. Now, just for comparison's sake, the actual value of root 3, if we take it to, let's say, 5 decimal places, is 1.73205. So you can see that this approximation has given us this correct to 3 decimal places. So it's a pretty good approximation. And we only needed a polynomial to do that. Now again, if we'd taken more terms, we'd have got a more accurate approximation. If we'd taken fewer terms, we'd have been less accurate. And also, the closer to 4 we get, the more accurate it is. We're always close if we're close to this value that it's centered at. But still, this gives us a pretty good approximation of root 3. Okay, and that's a nice use of Taylor's polynomial. Next time we'll see Taylor's series, which will help us give even better approximations and maybe even completely help us determine functions as a series. But that'll do for now.